In this video, I'm going to go through the process of conducting a hypothesis test for a single population proportion. And as with all these videos, I'm going to go through it once where I don't necessarily explain every detail. I just go through the process of solving the problem, and then I'll come back through it and fill in some blanks, maybe explain how things would be different if certain details were different. All right, so let's start by reading through the prompt. Today is the day after the Super Bowl, and this was kind of on my head, watching some of these commercials. You got to imagine that they create multiple versions of these commercials, right? And test them with people. They don't just run the first thing that comes to their mind. So let's say a company that is planning to air a commercial during the Super Bowl creates two versions, which we'll call A and B, of the commercial. And in order to determine whether one of the versions is preferable to viewers, they show both commercials to a group of 85 people and then ask them which they prefer. For each viewer, the order in which they determine the order in which they view the commercials is determined by coin flip. So from the group of 85 people, 52 preferred version B. Is this evidence that viewers prefer one of the versions? All right, so we start with step 0. In step 0, we're trying to figure out what process we need to do. The variable involved is categorical, right? The values of the variable are commercial A or commercial B. And in particular, we're only interested in one proportion, or in other words, this categorical variable, we only care about two values. It's either A or B. And so that means that this is going to be a module 5 type thing. It's going to be a one sample Z procedure. And the question we're being asked is a yes/no question. That is this evidence that viewers prefer one of the versions? Or in other words, we could say, do they prefer version B, or do they prefer version A, or something like that. So it's a yes/no question. And so that means it's a hypothesis test. And so this should be a one sample Z test for a proportion. So step 0, not really part of the actual hypothesis test, but a very necessary step. The problem didn't tell us to do a hypothesis test. We determined that that's what we should do. All right, so step 1 in a hypothesis test is to state hypotheses. Our null hypothesis is a little tricky. It's about as tricky as a null hypothesis can get, because you might say, look, it's always just P equals something, but it's not really clear what that should be. And this is a common thing that can happen with proportions. There's a very natural question to ask about categorical variables with two values that can be phrased in any number of ways, which is, which value is more common? And so if we're trying to determine, whether they prefer one version over the other, the boundary value that we're interested in is a half. That is, if in fact half of our population prefers version A and half prefers version B, that would be a situation where in fact no one really preferred, or overall there was no preference between the versions. So our null hypothesis is that P equals a half, and notice that a half doesn't show up anywhere in the prompt. So that's why it's a bit tricky. Our alternative hypothesis, well, we know that it's going to be P in 0.5, and then we have to ask ourselves, well, should it be less than, greater than, not equal to? And we realize as we're doing this, we have left out a very key detail here. What is P, right? Is P the proportion who prefer version A, or is it the proportion who prefer version B? Either way is fine, but since we're given information in terms of version B, I'm going to say that P is the proportion of the true population, right? It's P. P always represents the population parameter. So P is the proportion that prefer B. Now, as it turns out, that doesn't really affect our alternative hypothesis, because in the problem, there is no indication before they do the study that people prefer one versus the other, right? In the end, it looks like more people prefer version B, but our data does not influence our hypotheses. The hypotheses can be stated without looking at the actual data from the sample. And since we don't know what the preference is or what preference we should expect, right? We're not saying, oh yeah, we expect this version B to be better. Our alternative should be not equal. So that's step one, a little trickier than some instances. And there's this important thing to remember. Sometimes you have to define what the proportion actually is. That is, it's not obvious what it should be. So in step two, we're going to check conditions. And our conditions, the first two conditions are exactly the same as what we did for a population mean. We need randomization. Now, in this problem, you might ask, well, it doesn't tell us whether this group of 85 people is randomly selected, but this is not an observational study, right? The company doing this research is showing people the videos. This is an experiment. And so we can't really expect that this group of 85 people is randomly selected. So how might randomization be satisfied? When we have an experiment, what we're looking for is randomly assigning of treatment. And since the order in which each person views the two commercials is determined by coin flip, we do have randomization. This is a randomized experiment. Otherwise, we might have to worry, if we always showed everyone version A first, that the preference could be based on the order we showed them and not actually the content of the commercials. So this is a randomized experiment. So that's satisfied. We'll put a little check mark. We need independence. Now, we're not really told what our population is, so we have to make a reasonable inference based on what we've read. I'm going to say that our population is people who watch television. Let's say maybe people in the US. So let's say US adults who watch television. And our condition is just that this is much larger than the sample, and there are more than 850 adults in the US who watch television. So this is more than 10 times the sample. So this is satisfied. And you might have had a slightly different population. That's fine. We weren't given a ton of information here. Our condition on data. Now, the condition on data is actually relatively straightforward here. We just have to confirm that there are at least 10 successes and 10 failures. We have 52 successes. Right, that's a success is someone prefers version B. And that leaves, out of 85, that leaves 33 failures. So these are each at least 10. So our condition is satisfied. All three conditions are satisfied. And I should mention this. I'll come back to this when I go back through the video. This step 2 is not the way it's presented in the workbook. The workbook presents it with this mnemonic bins. And again, I'll talk more about that later. I prefer to look at it this way. I'm fine with either approach. That is when I grade this stuff by hand. If you confirm this using bins versus if you confirm it using this, that's up to you. I tend to think that this is nice because the first two steps are what we're used to, right? Nothing new. And then the third step, well, it's different, but it's in the same vein, right? We always have a condition on data. So I'll come back to that more after finishing the problem, just what these conditions mean and how they relate to bins. So we have hypotheses. We have checked our conditions. So in step 3, we have to do our calculations. And our formula for a test statistic is z equals p hat minus p naught over the square root of p naught times 1 minus p naught over n. So we need all of these numbers. The two numbers that we just have, right, that we don't have to do any calculations for, well, we know that n is 85. Lowercase n is always the sample size. And p naught, kind of like mu naught, is just the value that appears in our hypotheses. So p naught is 0.5. So those numbers we just have. P hat we have to calculate. And p hat is the proportion of successes, right? And so if you were wondering why is people preferring B a success, it's because we have to be consistent, right? If P is going to refer to the population proportion that prefer B, then P hat is going to refer to the sample proportion that prefer B. And so I want to be consistent here, and that means that people preferring B is considered a success. Doesn't mean that the company literally wanted people to prefer B. Success and failure are just terms for the two possibilities. So to calculate P hat, I need number of successes. So my number of successes, this is capital X, is 52. And so that means that P hat is the number of successes over the sample size. And let's figure out what that is. So I'm going to round this to 3 decimal places. And I'm actually going to come back to this later, this notion of how much we should round to, because this can definitely get tricky. It probably won't matter here, but I will address it. All right, so I need to calculate Z. So I'm going to write out what it is now. I have all the pieces. So P hat is 0.612. P naught is 0.5. And an important thing, in the hypothesis test, in this standard error at the bottom, the denominator here, I put in P naught, not P hat. It's a really easy mistake to make, but we're conducting this under the assumption the null hypothesis is true. So this is what I should type in. So let's type this whole thing in. I didn't mean to close that parentheses. Now we're going to divide by the square root of 0.5 times 1 minus 0.5 over 85. You got to be really careful with how you type all this stuff in. I get an answer. I get 2.07. We'll round to 2 decimal places. So I have Z. And now I need to calculate my p-value. Notice in this problem, there's a lot of p's, right? This lowercase p is the proportion that prefer B, the true proportion. P hat is the sample proportion that prefer B. P naught is the hypothesized proportion that prefer B. Capital P, or I try to write it capital to be consistent, is the p-value. And before calculating the p-value, I need to draw a picture. And hopefully, as we do more and more of these, you become more comfortable with this. My alternative hypothesis was not equal. And my alternative hypothesis is necessary to calculate a p-value. Since my alternative was not equal, what I want to know is the total area outside of, not just above 2.07, but I'd also like to include the area below negative 2.07. So this is the area I want for my p-value. And that means there's a few ways to calculate this, but the way I look at it is once I've drawn the picture, I know these two areas are the same due to the symmetry of the normal distribution, right? We're calling this Z because these values do follow a normal distribution. They're the same area, so I need to double them. And it's going to be easier just to calculate this one and double it because by default, RStudio tells us area to the left. And so the way I'm going to type this in is it's 2 times p norm of minus 2.07. And what do I get for my answer? I get 0.0385. So that's my p-value. Calculations are done. All right, step 4, I have to state a conclusion. And I do this a lot in these videos. I intentionally did not say in the prompt that this was a hypothesis test. I really like to emphasize that it's the question we're trying to answer that determines not the procedure. It's not something in the text of the problem, right? And so because of that, there's no significance level. I wasn't given an alpha value. And so I'll just decide on alpha equals 0.05. Right? We need to decide what a big and a small p-value are. And so choose this. Since p is less than alpha, we reject the null hypothesis. Now we have to state this in context. And I'll come back to this later too. It's going to be maybe a bit of a weird conclusion in context because it was a two-sided alternative. we have evidence that viewers prefer version B. And this may seem like a bit of a weird conclusion because you might say, wait, your alternative was not equal. You were saying that our alternative hypothesis was not equal. We have evidence in favor of the alternative. How can we say that we have evidence that they prefer version B? I'll talk about that when I come back through this. Notice if the conditions hadn't been satisfied, I would have had a third sentence here, right? So we always have our first sentence, statistical language, context, and then conditions. I didn't write anything because conditions were satisfied. All right, so I'm done. I've done the full hypothesis test. Let's scroll back up and look at some details. Okay, so I talked about step 0 at length initially. Whole idea here is it's a categorical variable. It's split into two options, right? Some categorical variables have more than two possibilities, and sometimes we just decide, hey, we're only interested in, is it this or is it something else? In this case, we just literally only had two options. So all the module 5 stuff makes sense. It's categorical with two values. And it's a yes/no question, right? It's is this evidence, right? That's a big hint to us that this is a hypothesis test. Yes/no question about the value of a variable. So we're going to do a one sample z test for a proportion. The big thing with hypotheses, moving on to step 1, or I guess a few things. With proportions, we should be careful to state what our proportion refers to. That will be something that we want to be consistent throughout the problem. And it doesn't matter, right? If I had decided to make P the proportion that prefer A, that would be fine. It would have changed things throughout, but as long as I was consistent with that decision, I would end up with the same P value. But you have to be consistent, and it's hard to be consistent when you don't remind yourself that you're making a choice. So I always like to write that down here. This is what P is. This didn't really show up with means, right? Because we had a quantitative variable, it was just the mean is what it is, right? There's no choice there. All right, so we had this additional little wrinkle here that really our boundary value is a half. And this is something that should be in the back of your head whenever you're doing a hypothesis test for a proportion. If you're looking at it and you can't figure out what the value should be, you should not just assume it's a half, but you should ask yourself, does a half make sense as a null hypothesis value for the proportion? Right? Oftentimes, that's what we're interested in. Is or is it not more than half of something? So if you have that in the back of your mind as something that's worth thinking about, then you'll usually find it when you need to. And then again, our alternative was not equal to, because in our initial prompt, we were not given any indication that 1 was expected to be better. Our hypotheses do not rely on the actual data we collect. Doesn't matter that from the group we tested, it seems that at least in that group, version B was preferable. That doesn't affect our hypotheses. All right, so checking conditions. Randomization and independence, you're hopefully getting familiar with. Remember, randomization, one of the big things I see people mess up is remember that we have two different randomization conditions if it's an experiment versus an observational study, right? In this case, it's a randomized experiment, or it's an experiment, and so what we look for is randomization of treatments. Here it was randomized because they randomly decided the order in which people watched the two videos. If it had been an observational study, we would be looking for a random sample. Our independence condition, it's all about telling me what the population is, and then telling me whether you think that's 10 times the sample. In this problem, there would be lots of good answers for the population, right? You could say people who plan to watch the Super Bowl. You could say, who knows, maybe they're really just testing this on people who might use their product, right? Maybe that was how they chose their sample. They were thinking of that as the population. We're not given a ton of information. Make a reasonable assertion of what the population is, and then tell me whether you think it's 10 times the sample. The condition on data, again, this is about as easy as a condition on data could be. What we do is we say, in the sample, did we have at least 10 successes and at least 10 failures? That's all we need to check. All right, so let's talk about this whole bins thing. Another way to look at this is the way the workbook does it, bins, which you determine whether the data is binomial. I do that in step 0, right? So I already kind of did that. And then we have our independence condition, our success rate condition, and so forth. And what it comes down to is ultimately, I'm checking the same things. I just like to split it up like this because two things. One, I think the step zero, it's important to remember that step zero is occurring before you know what to do, right? So you haven't decided this is a question about proportions. You shouldn't even be thinking bins, right? You're just saying, hey, what should I do here? And so that's why I put that into the step zero. It's because it's really before you even know what to do. And then I like to present these conditions in this way because it makes it consistent. Every single hypothesis test and confidence interval in this course will have the same three types of conditions: randomization, independence, and condition on data. And really, for the most part, it'll just be this last one that's ever any different. And so I think it makes it a little easier to keep track. In any case, if you, on a test, answer a question and you check the conditions by confirming bins, great. I'll give you credit for that. Any correct methods are always fine. So that's where the conditions, or why the conditions look like this. All right, so for step 3, I went through this computation, a few details. I think the biggest thing that you'll practice this a bunch, and in the end, hopefully the condition or the calculations aren't too bad. The one mistake I can see a lot of is putting p hat here instead of p naught. Easy mistake to make. They're representing the same thing in some sense, right? They're both talking about the proportion of people who preferred version B, but it is important that you correctly choose which one to plug in there. So I did this calculation, and then I used the alternative hypothesis, which is really important. You always have to draw this picture, or at least know what calculation to do, right? If you knew this was the calculation just because the alternative was not equal, great. But if you're having any trouble with this, I really recommend always draw the picture. And then when we got to step 4, we rejected the null hypothesis because p was less than alpha. And notice I said we have evidence that viewers prefer version B. Now, I think, and often the workbook does this, and I don't know that I would not mark this wrong on an exam. You might be tempted to say, oh, we have evidence that viewers prefer one version over the other, right? Because that was what the question was, right? Is this evidence that viewers prefer one version over the other? Here's the thing. Let's pretend I'm working for this company, right? And I'm doing some math for them, and they do this whole study, and they're like, all right, what did you determine? And I say, oh yeah, the viewers, they prefer one of them. That would be a weird answer, right? For a few reasons. One, why'd they hire me, right? If all I could tell them is the viewers preferred one version over the other. But two, it's pretty clear that the only thing we have evidence for is that they preferred version B, right? We don't need statistics to know that, right? You could have looked at this before this class and said, look, it really looks like people prefer version B. So the whole point of this calculation is trying to determine whether, maybe from like a real world context, whether they should do another study, right? Whether they should say, hey, maybe we need to get like 500 people and show them these commercials, right? They're spending, some millions of dollars showing a Super Bowl commercial. They might say, look, do we really have evidence that one of these is better, or should we look closer? And so the whole point of the two-sided alternative hypothesis is to force us to double our p-value in the end, which is saying, look, because we were willing to conclude either that A was better or that B was better, it's more likely, if in fact they are equivalent commercials, that due to chance, we would end up with a sample that seemed to have one prefer the other. And so that's the whole function of the alternative hypothesis. But in the end, the only thing we actually have evidence for is that people prefer version B, right? I mean, if in fact it turns out that people prefer version A, it's not as if we had done something right? I mean, our study very clearly only provides evidence that version B might be preferred. So as I said, kind of a weird thing, but it's a detail that I think kind of matters, because I like to think that in an ideal kind of write-up of a hypothesis test, this sentence, right, that's taking your conclusion and explaining it in the context of the problem, should be as understandable to someone who doesn't know statistics as possible, right? And if I'm thinking of this in the context of someone working at this company and making a recommendation on the commercial, that's the kind of recommendation that people want from me, right? They want me to say, yeah, this actually is evidence that version B is better. This would be an unlikely thing to have happened if in fact the two versions were equal. And so that's why I phrase it like that. All right, so that's a whole hypothesis test for a proportion. Hopefully, as you're seeing more of these, you're starting to notice these things that are the same and the things that are different, right? Because what you realize is that there's not a whole lot that's really different, right? In the end, I mean, step 0 is different because we're identifying, it's the same process, but we're identifying a different thing, right? Or we identify a different procedure. Our hypotheses are almost exactly the same, right? Except for what this symbol is. Our conditions are the same, except for the condition on data is different. Our calculations are different, but with similar aspects to them, right? Z kind of looks the same, and the way we calculate our p-value, same sort of patterns to it. And then finally, our conclusion, again, is the same formula to it. So I think it's important as you see more of these that you recognize this, that many things are the same and a few things are different. And you want to recognize which is which so that you can approach these as different versions of the same thing and not a bunch of different procedures. All right, so hopefully that was helpful. Thanks to those who watched the whole video. Yeah, I think this hopefully clears up some misconceptions or any spots where that you were stuck.